Good afternoon, everyone. Would you slightly take your seats? Move slowly, you had a lot of food. Great. Yeah, thank you everyone for being here at the second or third, depending on how you count, session of the Programming Local First workshop. And we'll start with a great talk by Carlos already. So this was meant to lure you back from lunch. It seems it has worked. Everything's ready? Then, Carlos, the stage is yours.
Okay, thanks. So try to make this an overview so that we have enough time for the discussion session. So
Outside the camera, if you
can... Okay, I'll try to see the slides from here. There's no mirroring coming on, so okay, but I think I can work from here. So is that okay now?
Yes.
Okay. So the talk's title is a question, and the answer is maybe. There are some solutions, but they're not 100% okay. And this is also a brief literature review where I'm going to show you several works. I will not be able to go into detail, but these works are kind of roads into answering these questions, so they might be interesting to see later on. So what's the connection from local first? So I guess the crowd here, we all want to go from client server to local first. We want the good properties of local first. I try to bring some from memory, so independence from network, faster response times, more control over data. So see, these are some of the nice things. But by moving out of client server, we also lose some things. So we no longer have the thin clients that they're just a presentation interface and a way to collect user actions. Client server is also good in terms of metadata. We have much lower metadata needs, so it simplifies. So I'm not saying that we go to client server, but we need to solve some of the problems by doing things local first. And also, I also noticed that upgrades are easier because if you have all the code in the server and you push it to the browser, it's very easy to do the upgrades. So, but we'll have to solve some problems. So, you all know from the CAP theorem that there is this tension between consistency and data availability. And in order to have high availability, we need to accommodate for divergence. And this is what we get also in local first, as we have seen in the previous talk. So disconnected clients can evolve their data independently and synchronize when possible. And we might have this fork join model where it's quite messy. But tracking divergence, okay, it's interesting, but it requires metadata. So I'll talk a bit about the impacts in terms of metadata. But how many clients are we talking about? So this is also important. So we might have millions of users, but we only have 3 or 4 interacting on the same state, okay? And in that case, we can kind of compartmentalize all these interactions, and our metadata growth will only grow to 4 or 5, the number of parties that are interacting. But we might have some applications where we need thousands or millions of users interacting. I tried to come up with some cases. So for instance, voting polls, where we want to accrue a lot of votes. Systems monitoring, if you are trying to see that observability, the behavior of the system, and do it in a kind of CRDT-based way. Social media, just collecting likes. Likes is just like collecting votes, but less important or even more important. And Wikipedia editing. So some pages have been updated by hundreds of users, and we might want to model that. So we might run into sessions where we have many parties that are interacting over the same data. So we have a problem here, is that metadata need is linear on the number of clients that are issuing the updates if they communicate directly, and we'll come to, that will help us later on. And okay, I'll be showing papers all the time. So this is a result from the 90s that tells you basically the same thing. So there is a linear relation between the number of actors interacting with the data and the metadata size, okay? So this is established. So now we might guess, okay, either we pay the price and we do it because we need to do it, or we try some workarounds. So the question is, are there workarounds? And there are some, and the talk will be about some of these workarounds. So impossibility results that are correct we cannot do anything about them. They are very useful, and they are correct, so there's no way around. But if we can tweak a little bit the conditions, we often find a way to do different things, but we need to kind of change the system model that is underlying to the result. So one way to change it is to not focus on how many parties are doing the updates, but on the number of updates themselves. So we could collect something called a causal history. So you can imagine for each update, I can create a unique ID, and then we just keep sets of these unique IDs, and we compare these sets in order to track which data has diverged and needs to be synchronized back. Okay, so we just have these sets of random unique IDs. If the random ID is long enough, we don't have collision. That's the birthday paradox, and we can keep working with that. So by doing that, we build something called causal histories. I'm going to talk about 3 systems that kind of built more or less on top of this. The other way is if we restrict the communication topology. So if we get what was talked in the morning, like referees, points where we communicate to a given special party, we can kind of tweak and restrict the communication topology, because the result only holds if we are interacting from all to all, okay? So if we restrict a little bit that, we can improve a little bit the metadata cost. So I'm not sure if this is the oldest, but this is the oldest reference I know about of using kind of hashes to track what's happening in the system. So this is in the track that we don't care how many entities we have. We care about the updates themselves. So this system, this is a paper from 2003. I don't want you to read the whole of the abstract, but the idea is that, okay, it's like a version control system. So you are changing documents. This is before JIT, I suppose. You are changing the document, and then you track the hashes of the resulting document, and then they build a graph that is connecting all these hashes, and this is what is used to detect when things need to be reconciled. It has a good property that since they are hashing the content, if 2 different changes end up resulting in the same content, they can detect that, and you no longer need to. These things are called like coincidental equalities, if I recall. So this is the idea. Then, sorry, there were evolutions of like doing systems with hashes. One is here from Martin. But before that, you already have systems like Bitcoin where we have hash chains. So in this case, if I got the gist of Martin's proposal, so what we have is this for a directed for a DAG, for the same properties for a DAG. Where does it differ from the previous system? Is that in hash histories, it was the hash of the content. Here you have the hash of kind of the update and the hashes of the things that preceded it. So you keep adding the hashes of the dependencies that you have together with the update, and you hash the thing together. And this way you get a system with the same properties that you get kind of in a blockchain, where you have this kind of self-certification of what is happening. So, but this is growing a lot of data, okay? This is a lot of data, but in some systems, you want to document what happened for auditing. This is all fine, but there's a huge metadata cost. So can we make these things smaller in terms of metadata? So we try to do a little bit of this in an MSc thesis. So the idea was the following. I'm going to have the abstract, but I'm not going to tell you in detail. But this is the gist of the idea. Like when we are comparing that, we might have parties that diverged a long time ago. So in order to compare data, we can look at these causal histories. Sometimes you call this a causal context. But if you are syncing very frequently, most of the causal context is in common between the parties. And if a party diverges for a long time and didn't sync back, probably you no longer want to incorporate those elements because they diverged from the system a long time ago. So we try to have a thing based on Bloom filters. It's a variant of Bloom filters that are kind of forgetting information all the time. So they only accurately track the most recent information. And the idea is that if you sync frequently, you might be able to just look at the most recent information to detect divergence, and then have a system that is not growing, not even with a number of updates in the system, like the prior one did that. Unfortunately, you no longer can have 100% accuracy. There is a trade-off. I don't think that the solution is perfect. There's a problem about merging Bloom filters if you have an open system where you don't know how many actors you have. So there's still research problems over here, but this might be a direction. So with this, I close the ones that are based on kind of probabilistic things and hashes. Now let's look at deterministic solutions. And I'm going to look at the two specific cases, that counters and that admin set. So I'm the unlucky person to be the first one to present a spec of a CRDT. So what do I want you to get from here? I'm not going into the depth of the math, but if you want to do a counter that works as CRDT in a given number of parties, it's very easy. Each party has its own counter, its own, how do you call it, single writer entry in the counter, and I keep updating my entry, and we collect the map with all the entries, and the end result is summing the image of the map, all the values in the map. Okay, this is very easy. What's the problem here is that we for any actor that tries to do something, we have one entry. So this is again linear on the number of actors. So what can we do about this? This is a problem. And so we did some work in 2017, even a little bit early because it took some time to publish. And it is possible to kind of do a multi-step protocol where I can register the account under a given identity so that I'm totally local first, I can operate without internet. But when I have connectivity, I will try to transfer this count to another party. You can think of it as kind of the special one, the arbiter, okay? And you get rid of your local data, and then we control the linear scalability problem. So we designed this system for like this can work for any number of tires. It's generic, but we thought about like we have end clients over here. You have this could be your content distribution network with all those points that we have seen in the morning, where we have places that are important enough to have their own data center, and then we might have the root ones. So the things are migrating from here to here. The idea is that we register under the same replica ID. Then we don't have server affinity, so we can have fault tolerance in terms of servers. So we can try to be transferring to one server, then to assign to another one. But in the end, this is an atomic transfer where the thing will only end up in a given server. And once the clients know that the thing has been transferred, they can remove and forget all the data that they have. They just need one counter. So we don't even need to have one data item per server or per entity we interacted with. So this is a rather complex protocol. I'm not going to explain you, but you see that's a kind of three-way handshake where we are preparing to do the transfer. And the end, we have something over there that in the end will be transferred into the account in the server, and you kind of reset everything in the end, and you forget all the information about what you did during the transfer. So this is one approach for counters. Now, there is a very interesting recent one that was presented in PAPOC. Maybe some of you watched this presentation in this year's PAPOC. The authors choose not to publish the paper. Probably they're going to send to another venue, but I have some highlights of the paper over here. So what you can do is, if you depart from the previous approach where you had this non-server affinity, so if you kind of crystallize the hierarchy that you have, you might be able to distribute each entry for the different nodes and then do some intelligent tricks that they do in the paper. So they form a binary tree, and then wherever you are, you have your local count, and you have the neighbor from your child from your left, on the right, and your parent, and you combine everything so that you have only one entry per node, no longer n entries reflecting the number of nodes. And the algorithm is very simple. It looks something like this, okay? Just want you to see that what they have. So you have this state over here, and you have different merges depending on, you can merge to the left, to the right, and from your parent. And then when you are gossiping, you are basically sending to one size the sum of all the things you got from the other places, okay? So I'm sending to the right what I get from the left, from myself, and from the parent, and so forth, okay? And with this, you get a very interesting solution, but over a static topology. But this is one thing that we know how to do. Now, we did even a different thing in 2017 called borrow counters. It works for counters, probably not for admin CRDTs. And basically, it's kind of the referee idea. Like, we have a difference between permanent nodes and transient nodes. In the permanent nodes, you create an entry that you will assign to the transient node, the transit node will do counts over there. You keep doing merges and receiving information. I don't have time to explain this right, I'm sorry. You keep updating, receiving information, and when the transit node is done, it will kind of crystallize what it's done. It will close its entry. And at that point, the permanent node, so B is transit, the permanent node can move this information over here to itself. So it's kind of similar to the initial system I told you about, but simpler to reason with. And this is, well, it's not being very used. I'm making some publicity with it. I think it's a very elegant design. Sorry that I'm one of the authors, but I was not the main author. It was one of the students, so I can really say that. This was not my idea. And it's really simple. And you can, again, tying with the discussion in the morning, you can use these things, these points where you have a referee to kind of simplify a lot the system and to work around the impossibility results. Now, going for sets, so I'm not going to explain this thing, but the magic between observe remote set or admin set is that each time you are putting an element, you need to assign it a unique tag. Okay? Normally we call this thing a dot. So you need to keep generating these unique tags. And if you generate these unique tags, you can generate it very simply by having the node ID and a grow-only counter that you get from the node ID. So you have this causal context over here. And if I'm generating the next one in node A, since in A I already have generated A1 and A2, now I need to generate A3. Again, what is the problem? We are linear on the number of nodes that are doing these kind of things, okay? So how can we circumvent this problem? So this is a even more complex spec that I'm not going to focus in detail. So what is the problem with scaling causal CRDTs? So each active item is paired with a tag dot, okay? And the causal context, that thing over here, that collects all the things that I've seen in my local CRDT, is linear on the number of replicas that were active and that communicated with me. Okay, I might not have known about it, but if I got information from them, it's linear with them. So we have this is like ongoing work. This is already working for a given setting. It was presented at a local conference. And what we try to do is the same trick that we did for counters, we do it for causal CRDTs. So we did it for admin sets, and this also works for multi-value registers and for remove win sets, although we don't have it working. So the idea is kind of this. So we add elements under the replica ID tags. So we have our local ID that we control. We can use it to be local first and add elements. Then, at some point, we freeze it, and we try to migrate to one of several servers. But while it is frozen, I can still keep adding again on the other state that I have that is not frozen. So we never compromise availability, okay? Even for adds and deletes. Even in the process of migrating to I keep calling it the referee, I'm always available. I can always do operations, but I register on a different part of the state. And then when the server incorporates new tags, it will create translation pairs. It's basically saying that what was known as A3, now in my server, is like S34. So we while we were growing horizontally in the number of different nodes, now at the server side, we grow vertically because we are creating more numbers for all the clients that we are serving to, okay? So this is kind of the intuition. When I get to see the translation, I can locally forget the local tags. So I get rid of the local tags. And this is something unreadable that shows all the process. From here, and I want to give time for discussion, I don't want to see all the detail, but I just wanted to see that I'm adding stuff. And while I'm in the process of transferring, I'm also allowed to remove information. And then when I'm removing, I'm doing stuff on my local tags. But when I see the translation, I can reinterpret the removal based on the translation that I receive it, and in the end, everything gets okay. Okay, so we have a running implementation in Rust, and we compare the runs with a standard addable win set. So addable win set, if we have this number of a lot of servers, it grows a lot. So this one here, we are doing operations on a standard set. Here we stop doing operations, but then we keep synchronizing. So this lag there's a little bit of time where the system is getting to know all the other things that it didn't know new from the other replicas. This is why it still grows a little bit. But with this protocol, we end up doing all the transfers. We get rid of the metadata, and it's much more compact. So I didn't want it to show you work that is solving the whole of the problem. I want you to see that there is a problem here. If we have many parties interacting, there are some ways of trying to address it, and I'm sure there are better ways that still have to be found. So now we have time for questions. I have 2 possible questions that I'm already making if you are short of questions for the moment. So thank you.
Thank you, Carlos. That was very inspiring. I'm asking myself, also given what we discussed before lunch, so if you have an ensemble of replicas of a database, you use some protocol like Paxos or Raft to pick a leader and then make decisions that are consistent. Now, we don't do that in local first applications because we don't want this leader somehow. Now, it seems to me that picking a leader for some things, like topic-based here, is still the way to go. How do you see this?
I think it's even better because you don't need to agree on the leader that you are picking. So these 2 protocols that I've shown, the one for state and the scalable eventually consistent counters, you don't need to have server affinity. So you have several potential servers, and you can start interacting with them. And at some point, your interaction with that server will create some placeholder there that you will know about, and that you will be able to transfer information to that server. But at any point, you need to coordinate the choosing of the leader. So it's always a kind of, actually the communication protocol that we run is kind of CRDT-based protocol, where I show my state to the other party. You see my state, you evolve your state, you show your state back. So there's no leader election in the process. So
that's awesome.
Yeah, so that works, at least for counters. Walter?
So what you call a referee is sort of a coordination point.
It's a coordination point. Yeah, I was trying to connect with the morning talk. Yeah.
So that will eventually lead to loss of availability if this referee doesn't synchronize the operations or doesn't make any decision to the world.
So it depends. So for the counters, when we do the let me show you the other one. No, I can go to the counters. So only when I see, I'm always resetting my local information when I see when I see that this server that I'm communicating with reflected the data in its own state. Okay, only at that point. And at that point, I can get a copy of the data from the server. So for instance, for counts, I'm moving from the count under my ID to the count under the server. And the server will increment its own entry. Only when I see that, at the same time, I'm storing a local copy of the server's entry with myself, and I'm resetting my old information. So I never lose the data that I accepted from my user.
Yeah, but you rely on the referee accepting your operations to be able to synchronize them with the world.
But I don't have affinity. Mm-hmm. So if it's not communicating, I can start interaction with another one.
Okay, that's the good point.
Is that idempotent? You can interact with 2?
Sorry. Yeah, so the whole protocol is idempotent. So the whole protocol is, we don't have a name for this. This is almost like CRDT protocols. I'm always showing the state. So all this protocol is immune to reordering, data loss, and data duplication in any order.
Okay.
Okay. So it's kind of, actually, the consensus protocols, I think they also have a little bit of that underneath, okay? Sure. So in order to be reliant to the network errors.
So it's been interesting to see you run through almost like a zoo of algorithms for optimization. Mm-hmm. And I'm curious how much you think about choosing these algorithms in the context of particular applications, or certain applications and the topologies of those applications that would be tailored towards certain algorithms versus others, and how you think about parameterizing these algorithms and almost like parameterizing the choice between these algorithms in a way that's accessible for application developers.
Yeah. So these algorithms, some of those, especially the transfer ones, are very complex. So there's some parameterization based on the system model. So if you go, okay, the hard way, you go and read the paper, see the system model. If your system matches the system model, you know which one. So I think, for instance, the tree-based one with a fixed tree is very interesting, but like unless you put more functionality for the capacity to rearrange the tree, it's going to be brittle probably. I'm thinking in background that there is a very nice protocol also from some other colleagues from Lisbon. It's called the Plum Tree Protocol that is used in industry also. It's and where they are always trying to rebuild a tree, but they fall back to a graph if there is any problem. So they're always operating on the graph and rebuilding a tree if things break. So it might be possible, this is a very like soft conjecture, to combine that topology idea with things like the Plum Tree Protocol. So that is one way to go. On these other classes of protocols, they already allow multi-tier, no affinity, but you still have some things that you need to calibrate, like how many servers you want to have in each tier. And there are there are reference implementations, but there are no one did a usable thing for the industry yet. So it's still an open terrain.
So is that why you couldn't have everyone be a leader because you have only a fixed amount of servers, or what else is stopping just everyone becoming a leader and being a...
So what you are trying to do is, when you are rewriting IDs, you want to move from a very big membership into a smaller membership, okay? So this is the idea of having an hierarchy. And these hierarchies happen in all large-scale systems. Even for, like when people build like Bitcoin, it's like everyone is going to run their own peer, but in the end, you have all these places that run it for you.
In the end, it's a centralized system, yes?
Yeah.
But that's a different topic?
But but again, I'm no fan of this things, but...
I do.
But no, but what I like to say is that I think that's hierarchies emerge when you are dealing with complexity in society, like in cities, everything.
So if I got you
so you need a little bit of both.
So if I got you correctly, basically, if everyone were their own leader, you couldn't compress the IDs anymore. But,
yes,
but,
probably.
But the protocol would still work just without compression.
So, So one thing that I forgot to mention is, so for instance, in the protocol that we have, it's not totally local first in one thing, because we only deal with interaction from the client to one of many possible servers in the upper tier. And talking with Martin, he raised the thing that, okay, but we also want to be able to cooperate within the same room. So we are trying to improve it, work on that thing. But for that, basically, you need to, some point, to expand the number of IDs that you see, your local collaborators. But then you need to have one doing some kind of garbage collection so that it will get rid of all those IDs and replace them from a upper tier ID so that you are not going to pollute forever the namespace in the system. So that is kind of the idea.
But could you select for a room locally just a leader? Would that work?
That will work, and these things happens in like cluster heads and things like that in ad hoc networks.
Further, yeah.
So in the setting where you have a large number of clients and a smaller number of servers, I worry that since you've got a large number of clients, some of them might not be following the protocol correctly. And so you gave this example of social media where it's counting likes and what is to stop me writing a client that adds 10,000 likes to my own post in order to boost things. Do you have any thoughts on that sort of Byzantine behavior, how that might factor into these algorithms?
Yeah. So I totally agree that this is a very important concern. That should be because we have lots of clients on those circumstances. We didn't do anything about it. And I recall when I was playing with the Nutella network that there was a lot of attacks being done by people just fiddling with the code and saying that they had content that they didn't have and things like that. So it's a very important concern that we haven't dealt with, and I don't really know the total implications of dealing with that.
Yeah, the old peer-to-peer file sharing networks probably have a ton of lessons now that you mention it. But that was BitTorrent's thing, right? That was why BitTorrent won, is they started self-signing all the data. Right, so you couldn't spoof because you had to have the data. I mean, you could just say you had things you didn't, but you couldn't say you had something and send something else because they'd catch you.
So
That's the Merkle trees.
yeah.
Yeah.
So some thoughts I have on that, not too long, is like for CRDT things, is that it's very hard to constrain. So you can do something Byzantine, say, on the server side, where you have like a Byzantine majority on the server side. If you trust on the clients and they have like keys that you trust, you can kind of build these protocols for the server side. One thing that is very hard is if you don't trust the clients, what are you going to do? Because how do you constrain how much they can kind of ruin the system? So you need to have kind of provenance of what any client did so that you can then remove it. And I think there's works going in that direction.
Sorry, I don't see. Oh, yeah, this is UCAN, right?
Yeah. Thanks.
It's a perfect segue. So this thing I mentioned in the morning after somebody's talk of, I made passing reference to submarine sealing. It's actually pretty similar because we have a rooted authority that's delegating. You have the whole provenance, and it basically gets, the whole certificate chain gets rolled up. And so as long as somebody has more capability than you, they can basically take your rights under their authority, but not vice versa. So you have scarcity now, where it rolls up to the top. So I'm very much looking forward to reading this paper because there might be some interesting stuff for us to do.
Okay, so yeah, I understand the description. So the other thing I've seen is the systems where you need to have another majority to certify each update. So it's a different approach, but yours means, I think it looks even more controllable because you already have that hierarchy built in, and it's not just a majority that will accept that given client operation.
Yeah, well, it's two things. You already have this hierarchy, and somebody higher up in this chain must have equal or more authority than you do. So there's a higher degree of trust as you roll up. Yeah.
Okay.
Great. I think this puts a lot of time for questions.
Okay.
Thank you very much for your great
Okay,
talk.
thank you.